I'm going to move on to Dr. Lee's second intern of the summer, AJ Dale. Thanks again, Maggie.
Yeah, thank you, Maggie. Great job. Very proud of you. The next speaker is AJ Dale. I had the privilege of being his mentor this year as well. AJ is also an amazing student. He showed a huge amount of initiative and creativity in approaching his problem, which I will let him describe to you. But AJ too has a bright future. We plan to publish what we have worked on. We've achieved an interesting result that AJ will tell you about, and this too will be a referenced work in as we continue with our project and the research that's tied to it into the future. So go ahead, break a leg.
AJ, if you're speaking, we cannot hear you.
Sorry, apologies.
There you go.
Okay, let's redo that. Sorry. Uh, Hello, my name is AJ Dale. My mentor was Dr. Pascal Lee, and my presentation is about a tethered balloon system for Mars. Uh, for a brief intro on it, Mars tethered balloon MTB experiments began at NASA's Hot and Mars project on Devon Island in the Arctic in 2000, but was continued in 2022 by Pascal and his peers. It served as Dr. Pascal and his peers uh, served as a baseline for my project, and while it worked as a very good starting point, it had many unaddressed details that I had to cover in my research. And the objective I had overall was to design an MTB system for future Mars base and rover missions. What its usages are include come from the fact that while we have camera footage and images from the surface of Mars, from things like the Ingenuity Martian helicopter or the rovers at a lower elevation of a few meters, and we have high orbital imaging from satellites such as the Mars Reconnaissance Orbiter of hundreds of kilometers in the air, the balloon mechanism would allow for imaging from only a few hundred meters, allowing us to have a better surveying of the land around whilst not being hundreds of kilometers in the air. And besides just imaging, it also provides a comms relay similar to a radio tower. It allows for environmental monitoring of both the surface and the atmosphere of Mars, and also works as a general visible beacon for those in the surrounding area to know where the base or rover are. The main question and requirements that we had, first off, was is a tethered balloon even plausible for a stationary base or mobile rover operations? And if so, what would the design be? The design would have to fall under the requirements of being able to carry a payload of at least 2 kilograms, must be able to survive the harsh Martian environment, such as winds, dust storms, temperatures, UV, etc. Must be able to operate without on-site human intervention, must stay airborne and functional for at least a full Martian day, and it must be able to fly 100 to 300 meters above the Martian surface. As for resources, first off, since this was a very design-focused project, Fusion 360 was my computer-aided design CAD software of choice. I had to do a lot of online research, and Google was what I used as my search engine. I used Google Gemini to help consolidate data, help me find sources, and especially to fix errors in the CAD when I encountered them. And lastly, Dr. Pascal Lee helped me a lot to have some feedback and clarification about the project, as well as brainstorming my ideas. And my friends and family, I was able to bounce ideas off of them and discuss what I thought would be some good ideas, and that provided some nice brainstorming feedback. As for researching my initial design, the main two things I found for stratospheric balloons or similar mechanisms were superpressure balloons and zero pressure balloons. The difference being that a superpressure balloon maintains around the same pressure inside of it, while a zero pressure balloon has a similar pressure to the atmosphere surrounding it. And this results in zero pressure balloons not being able to stay in the same elevation as much. So I decided to stay on a super pressure balloon, which has these unique lobes, which also help reduce stress due to the pressure imbalance. And since there'll be a weight under it, it'll also have a more teardrop shape, similar to this image here. And this was what my final design looks like. It, as I mentioned, has these lobes here, and it then tapers down to where there is a small cone on the bottom, which works as a valve point for the inflation mechanism, as well as helping to guide the entire balloon down a large conic dish here. That would then lead to the inflation mechanism that has two spherical pods to hold liquid hydrogen, since the balloon is held up by hydrogen gas. And then here's the balloon without without the cone or anything else, it just by itself. As for the carbon fiber cone on the bottom, it is connected to the envelope of the balloon via a simple collar that would then be screwed in and hold it against the envelope via tension. It is also has a carbon fiber ring where the instruments would be attached to, such as cameras and other monitoring mechanisms. And it goes down into this cone here, which has a poppet valve. It has not shown a cross-slit valve, and then a six support mechanism here. Half of it is not shown for the sake of showing the inside, where there would be a spring which would then hold against the poppet valve. As mentioned previously, in the end we used a poppet valve, since the poppet valve allows for the air to flow straight up, push the poppet valve upwards, and get into the balloon, whilst when the air is not flowing in, it'll just fall back down and then self-seal with air, and it won't hit the walls like a ball valve would due to its bottom stick. And then it also has a cross-slit valve on the bottom to block dust from getting inside, since it allows for things to come in when it's opened up, but not the other way. We originally considered doing like a basketball valve, me and Pascal thought, but then I soon discovered that that would not work due to those needing like to be made out of rubber or things like that, and those materials do not work at the high temperatures that are on Mars. As for the materials, the main balloon is made up of a mixture of a linear low density polyethylene, a metallocene linear low density polyethylene, and then metallized mylar slash PET. This allows for it to all melt together well. It has a high tensile strength. It maintains its shape. It has good UV protection, good tear protection, and it is not very permeable. As for the tether line that holds the balloon to the ground, to the base, to the rover, it is made out of Dyneema, which is extremely strong fiber. And the tendons are made out of Vectran, which are just a high tensile strength with a material that does not have permanent stretching, and both of them have a thin LDPE jacket infused with carbon black to help protect both of them from UV degradation. And lastly, as I mentioned previously, the cone is made out of carbon fiber, which is just strong and lightweight. After looking at the CAD, I created a regression based on the max balloon diameter to model the max payload mass for a given site elevation. This included creating a regression for the surface area, the tendon length, and the volume of the balloon based off of the diameter, and those were to fulfill the different variables in this equation here and this equation here to leave just the max payload mass as the dependent variable, while the diameter was the independent variable. And this revealed that a pumpkin balloon with optimal conditions, i.e., being in Hellas Basin with an elevation of negative 8.2 kilometers at its deepest point at the best time of year where the pressure is the highest, would still require a diameter of 13.87 meters to lift 2 kilograms 100 meters, which not realistic for a rover. It can be okay for a base, and that point is shown here, where the payload mass increases as the diameter increases. There is an alternative of a teardrop design. which, while structurally weaker due to the lack of tendons, has a significantly reduced mass and therefore diameter required, only requiring a 6.75 meters of diameter to lift 2 kilograms 100 meters, which, while better for a rover, it's still not the most practical. And as mentioned previously, since the 13-meter design is okay for base, this is also okay for base operations. This leads us to the conclusion that while a standard tether balloon is viable and for a stationary base, it is not viable for a rover, since as these two images show, this is the approximated size for a crewed rover, and it this would be the whole uh, dish that would hold the balloon would be larger in size than the entire rover, and especially so for an autonomous rover. So you may be asking, what's next? Well, first off, weight reduction would be the best goal because that reducing the weight would allow the diameter to be reduced. And so this could be finding better materials or finding better shape optimizations. And including shape optimizations, maybe having some things like a helikite to help make it like flow better through the air, or a capsule-like design to help it, while having the same volume, may have less horizontal footprint. So then it doesn't need as wide of a dish. And speaking of a dish, you could design the rover around the balloon. For instance, something that we thought about near the end was a kind of pedal dish, which would have multiple, instead of one conic shape, it would have multiple separate pedal-like uh, parts that would then open up when the balloon is come down to inflate. And then when the balloon is either deployed or it's deflated, it would close up, which, while it would help with the footprint, it would also add weight to Sudsea to design around that. And lastly, our tether line is quite heavy. It's being about 1.2 kilograms. So finding better optimizations for that would also be great. And lastly, because this was all in a design process and more research focused, and due to its large scale, I could not do very much, like no physical testing. So that was a very crucial step that still needs to be done regarding my designs. I thank you for allowing me to present my work, and a big thanks to the N3 program for giving me this opportunity, and especially to Dr. Pascal Lee for mentoring me throughout this entire thing. Any questions?
Right, well, that was really cool. I'm really impressed that you researched all those materials as well as just doing the design, because of course, designs are only good if you can actually make them.
Hmm.
So that was quite the complicated design. Really cool work.
Hmm. We went through a lot of different materials and parts of a design, but for time constraints, kept I didn't mention all of them. Yes, someone's raising their hand, so I
Yeah,
can't really see very well the presentation mode.
Hi. Hi, I'm Dr.
Hello.
Purvis. Hi. I really enjoyed your presentation.
Mhm.
Great job. I want to
Thank
know,
you.
like, you had different like stages to your project, like different parts. What was your favorite part?
I would say my favorite part was designing the envelope itself because when I originally did it, it was really fun in to just have the CAD up and figuring out the unique shape and working with the sketches to make that design. It felt really fulfilling to make this very unique looking design that is, while it did have a lot of errors and would break a lot in the CAD, was able to get that working. It felt very satisfying to get that working, and that was, I would probably say, my favorite part.
Awesome. Thank you.
Any other questions? How would the balloon deal with harsh dust storms on Mars? In regards to wind, uh, this was a thing that I actually had a misconception about at first. Is I thought that based on the original experiments on Earth on Devon Island, wind was a very significant problem where the balloons would get flown around, would get like tossed around and hit the ground. But then after talking with Pascal about Dr. Pascal Lee about this, that I was told that because the atmosphere of Mars is so much less dense and it's so thin compared to Earth's, that even if the winds are a lot higher, their impact is a lot less on the balloons. So it would not get tossed around nearly as much as it would on Earth. And in regards to the particles in the air, I specifically chose materials that would be able to withstand that. Like while they could still tear due to them being thin, they're able to deal with that pretty well. Any further questions? Or is that all? Take that as a no.
Yeah, that's
Thank
just
you so much,
about all
everyone.
we have
And
time
yes,
for. So if you have other questions for AJ, they can answer you in the chat.
thank you so much.
Thank you so much.
Great job, AJ. Very proud of you too. Good job.
Thank you.